Okay. Yeah, so today I'm just going to talk about a study that our group has been doing over the past several months regarding essentially generating dense packings of faceted particles, in this case the platonic solids, via geometrically confining them. Does this work here? That's okay, I'll just use the laser. So we, already in this session, like we've talked a lot about clusters, and I thought I would just go ahead and kind of motivate like every feature of the study that we're doing right now. So one of the reasons that we're interested in finite packings generally is that this is basically a cluster system, and physicists have been like really fascinated by clusters for like half a century or more. And one of the reasons that they're so interesting is because they represent kind of like locally preferred motifs that a certain system might have, and whether or not these motifs are commensurate with like bulk structure has some bearing on whether the system can like successfully assemble into its bulk structure or whether there are barriers for that. So this is a really like kind of classic case of if you have spherical particles, right? So in the Cambridge cluster database, if you have particles that are interacting via some kind of Leonard-Jones potential, the locally preferred motif is actually icosahedral, and this fivefold order is totally incommensurate with the bulk structure. So there's some frustration there. And also, I just thought I'd throw in to try to tie into the theme of the conference that clusters represent manageable system sizes for developing like analytical tools. So the phase space of these guys is like kind of tractable computationally, and you can really apply energy landscaping and stuff like that to these systems in a way that doesn't kill your computer, maybe. I'm not sure. Need to be confirmed. On the more like application side of this, there's a lot of really interesting applications for clusters of, first of all, even just spherical particles. People are really interested in them to produce colloidal molecules, or using nanoparticles or colloids to basically create building blocks that can then be used to build structures hierarchically, really as like molecules in this sense. There's also interest in using clusters as like information storage devices. So these guys would have a certain set of states that the cluster can kind of transition between, and in that way do like computation. And kind of very recently, well, somewhat recently, people are really interested in clusters of metallic nanoparticles or like metallic dielectric nanoparticles because they have surface plasmon modes when you shine light on them that have very unique optical responses in the presence of light. And because these geometries are now basically on the order of the wavelength of light, when you change the cluster geometry, you can tune the optical properties of what you see. So in 2D, this has been studied a lot, but actually recently, experimentalists and theorists have started getting interested in three-dimensional plasmonic nanoclusters. Because so this is something with icosahedral symmetry. And if you have like a certain type of symmetry, you can actually create something called a metafluid, or they hope that you can create something called a metafluid that has like an isotropic optical response. So no matter the angle of incident light that you shine on these clusters, the optical response is relatively the same as the angle of light increases. And then you can just throw all these clusters in solution, and then you have a fluid that actually has a tunable optical response. And especially in the plasmonics industry, people are starting to get, or the plasmonics field, people are starting to get interested in the idea of building nanoclusters out of now faceted metallic nanoparticles. So experimentalists are already becoming very proficient and really good at generating faceted nanoparticles, like cubes or prisms in this case. And theorists and experimentalists now are becoming kind of intrigued by the possibility of like the field response around different junction geometries of faceted nanoparticles. So depending on whether these cubes are lined up face to face to edge, or edge to edge, that has a different optical response. So that's another kind of knob that you can turn to build like a metamaterial. And this is like a recent study where people have confined silver nanooctahedra in like cylindrical wells, and done some, I think they did surface Raman scattering, and measured like the enhancement factor of the field that you can get with these various cluster geometries. And so the numbers here correspond to these numbers. And they saw that, yeah, you can get enhancement, kind of significant enhancement of the field around these clusters, and it really depends on the geometry and on the contact types between particles. And I'll just now motivate maybe why we would choose to use like spherical confinement in our computational study to generate these dense finite packings. So about a decade ago, the Pine group and now the Manoharan group at Harvard developed this way of using emulsion droplets of like oil and water, or even water and oil, to confine colloidal or nanoparticles on the surface of the droplet, and then evaporate out the material inside the droplet and create like a whole class of structures that maybe is slightly different from a class of structures that you could get with attractive forces. So spherical confinement is a way of producing kind of like another set of classes. And so there's a reason, and this is just a scaled up, this is a very recent study out of Van Blotteren and Dijkstra collaboration that demonstrates that this can be scaled up a lot. So there's reason to basically be interested in the following kind of more theoretical question, which is, what is the set of finite structures that results from packing faceted particles inside a sphere? And we can choose to basically attack this via simulation. When we looked through the literature for this problem, to try to make sure that no one had already done this, because it seems like someone should have done it already. It turns out that there's actually, in the field of operations research, which was a field that I wasn't familiar with, there's a ton of work that's been done, like a ton of work. This is just a small sampling. It gets very specific, on packing circles inside polygons, circles inside circles, polygons inside polygons, etc. Sorry? Yeah, actually, I know why they say. So in operations research, there's a lot of interest in, so they call this container loading. And so the idea is maybe you would want to pack a container most efficiently or something for like food storage or transportation. They also give reasons like if you wanted to like decorate a region of land with like cell transmitters to produce like the most efficient cellular network, you might need to know how to pack circles inside various geometries. So there's a lot of ways that you can motivate this, I think. I drank the Kool-Aid. I basically bought into it.
Is it a tough problem to pack equal squares into a bigger square?
I didn't read this paper.
Okay.
Probably, yeah. I mean, I'm sure that it's not what we think, right?
Especially if the sides are not really
It says, oh yeah, exactly, right. So if you can't produce a perfect square lattice, then that would be a big problem. Yeah, exactly. When you move to like the three-dimensional community, which is what we're interested in, it turns out that mostly people almost exclusively have just been looking at packing spheres inside various geometries. And
Is this like thinking of sequential packing, or are you shaping them, or are you just like putting them in and seeing whether they...
how these guys do it? So the way that these guys do it is, this is a constrained optimization problem. And so because these are mathematicians, it's like, I think there are a few conjectured solutions, but for the most part, it's a set of, I think it would be like nonlinear equations that you have to solve simultaneously, and there's a set of constraints. And so they've developed like super fancy algorithms to try to...
It's not sequential loading, it's just you're looking for like some equilibrium possibilities.
Yeah, and they, you know, some of their algorithms, like, they do, you know, they match up to what might happen physically. So they do, there's like a rattling algorithm that would basically like perturb everything and see if they can quench it to like a smaller configuration. This one paper was the one paper that we found where people were packing non-spherical particles into a spherical geometry. So they looked at n equals 1 to 20 cubes with their algorithm, but so they couldn't really do any more because it was taking up a lot of compute resources. So here's how like we decided to attack this problem. Oof, the coloring. We looked at a class of faceted particles. So in this case, just the platonic solids, along with spheres, just for control, because that problem of spheres inside a sphere has been studied. And for n equals 4 through 60 of each of these particles, we constrain them inside a spherical bubble. So this is via Monte Carlo simulation that has a constant number of particles, pressure and temperature. And these are hard particles, so they have no energy. They just can't overlap with each other. And then we would ramp up and they can't overlap with the container whatsoever. And then we would just ramp up the pressure pretty slowly to some kind of maximum value. And this is like the density of the system inside the spherical bubble.
The centers of the polyhedra or the faces cannot overlap with the bubble?
So we were able to cheat in this case, and the overlap criterion that we implemented said no vertex of the particle can overlap with the bubble, right? Because these are convex. So we were able to say, yeah, it's completely constrained inside the bubble if no vertex overlaps with the bubble.
Overlaps or necessary.
Mm-hmm.
So it seems that there's a little glitch, where the middle arrow is pointing to. Is that a real glitch, or is that just...
This guy? I sometimes hesitate to show this picture because I feel like it's indicative of something that I'm not sure is real. But if you look at the movie here, let's see if this movie plays. So this is this system. So this is a system of like 21 octahedra. Takes a little bit of time, but it's kind of proceeding through higher and higher pressures. And then there's a moment, here's the moment, where these guys realize that they kind of realize that they can form this dodecahedral motif. It's really, I think it's beautiful. I've been studying this for too long. But it's like the centroids of all of these guys form a dodecahedral shell around a central particle. And I think this point here is basically when they realize that 5 of them can kind of fill a solid angle.
It seems like below that point, like every single tetrahedron is rotating freely, and then they stop rotating. It seems really clear.
Yeah, so the thing is, like, I don't even think I'm in quasi-static equilibrium. This represents a fast quench to high density. And so I don't really want to talk about thermodynamic properties of this system. Do you know what I mean? Like, so I'm not sure if I can talk about, I want to talk about that, but I don't know if it makes sense to, like, I don't know, discuss entropy along this line or anything like that.
Different ramping rates?
I did try that for a long time at first, and I basically chose one that produced, so for every state point here, we did the compression scheme 50 times, and then just basically chose the densest configuration. And so when we were kind of changing various parameters at the beginning to try to figure out what would give us the densest thing with minimal computational effort.
Does the location of that glitch depend on the ramping rate?
I haven't looked into that. Yeah, I don't know. This glitch isn't always here. So this glitch is present for this system, which is special, which is great. But like if you have 20 tetrahedra, for example, that want to form an icosahedron at the very end, that's smooth. So it depends, I think.
But you really need to ramp, right? You could just sample at various points along the
Yeah, I did. Yeah.
like an umbrella set.
Yeah, I tried to do that, and that was interesting. And then we decided to go this route, but I think that's something to visit in the future for sure, because that's kind of more thermodynamically sound anyway. Yeah. So now I'm just going to kind of briefly show some of our results and some of the patterns that we found in our results. And I can also try to plug into the main theme of the workshop by saying this is a lot of like raw data, and we could really benefit from like some kind of database that Simon's going to talk about soon for kind of correlating the set of data and making it available to everyone. So this, just to look at spheres for a second, this is a set of structures that I think we're all fairly familiar with. This has already been found, and you can find the point group symmetry for all of these guys. And you can see that it varies significantly from n equals 4 to 10. And then if you go to n equals 4 to 20, the same thing is kind of happening. There's a lot of different symmetries. We just colored the central particles red in this case.
So those are,
Oop.
this is the spheres confined in a sphere.
Yeah, so this was...
They,
Oh, you're giving away my big reveal. Yeah. It's that, yeah, this is... But it's not exactly, but it's related to the Tammy's problem.
so this is not reproducing what's already known in the literature?
This is reproducing what is known. But as soon as we did this was great because it helped us really put into perspective some of the actual new results. So these are some of the clusters of spheres that, like Pablo said, are basically known. And something to think about is that like some of these are a big mess, but some of these are completely beautiful. Like, so this is the 38 cluster that David was talking about earlier. So spherical confinement produces symmetries. It really selects for densest clusters that have a great amount of symmetry. And when you move to clusters of icosahedra, this is just our raw data again. And you can see, compared to spheres, some of these structures don't change at these values of n, right, as you move across. I'm going to talk about that more. Same thing with dodecahedra. When you look at all of these clusters, there's a wide variety of point group symmetries going on here. And even at higher n, there's some great cluster symmetries that seem to be selected by the spherical confinement. Sometimes it's, a weird thing, but a lot of the time it's not. If you move to octahedra now, you can kind of see it's becoming more and more of a, not so symmetric kind of situation at higher n. But even for small n, there's still a lot of symmetry. For cubes, it's a new class of structures, right? And for tetrahedra, it's especially messy down at higher n, but at smaller n, there's some interesting things going on.
How confident are you that the larger results are really important?
Not confident. Yeah, I didn't say densest. When I presented the topic, I just said dense packings. Yeah, I am not.
Maybe why they're messy, because the principle of maximum symmetry says that by and large, you should see high point group symmetry.
What system was, yeah.
Yeah. They don't want, well,
The larger is spherical.
no. But that principle can be applied to continuous symmetry measures. So it can still be used for things that are C1 symmetry. If you can invent a metric that is continuous symmetry.
Yeah, maybe we can talk more about that.
Let's discuss that.
Yeah, because my kind of intuitive understanding of the situation is that there's no possible reason that tetrahedra would want to pack inside a sphere in a way that was nice.
Well, I would suggest trying to formulate it in terms of continuous potentials and taking a limit, and then we could use baseline for it.
I would love that. Yeah, Yeah, this is just based on overlap checks, but the way to get more analytical is...
I think I know what
Cool. Yeah, thank you. This was the way that we chose to kind of parse more of the data. So this is just for the set of spheres from n equals, again, 4 to 60. And we can just take a look at the density profile as a function of n for the entire set of packings. And so the density in this case is just the volume of the particles with respect to the volume of the container. And something to note for spheres, so again, this is work that had been done before, but to note there are certain values of n at which the density is a lot higher than the density of its neighbors, right? And so we're calling these magic numbers kind of in deference to the cluster literature. And also the other thing to keep in mind here is that as n changes, this is the crystal class that each point group symmetry belongs to. So we're coloring it based on that. And so the crystal class changes drastically from n to n as you increase in n. So as you're trying to add like more and more hard spheres into your container, it's basically shifting around and producing a cluster that has a symmetry that's very different from the symmetry of maybe at n minus 1 for this problem. This is speaking of like busy slides. This is pretty good. So you can basically line these up on top of each other for all of these different particle types. So these are the two most spherical platonic solids. And you can do a similar kind of analysis. And something to note here is that we see some developing patterns in the data. So at certain values of n, the crystal class is the same. And indeed, even like the point group symmetry usually is the same for these clusters. And at certain values of n also, the magic numbers are the same, right? So n equals 6 is the same for all of these guys. And also, even though these are, especially the dodecahedron, it's a very faceted particle. It produces clusters that have a wide range of symmetries belonging to a wide range of crystal classes, which we found interesting. For the less spherical particles, you don't have maybe as much of a variety of symmetry, or even as many especially for the tetrahedron groups that are highly symmetric. And also the magic numbers aren't really lining up with each other. But there's still kind of a large number of symmetric clusters. And something that's interesting here is that, which you would expect, like the symmetry of the constituent particle is related to the symmetry of the cluster motif, especially for these super anisotropic particles. So because this is like a cube, right, it's producing clusters that have cubic or a subset of cubic symmetry. When you actually look at the magic number clusters, so I should point out the way that we're defining magic number clusters is essentially phenomenological. So it's based on a cutoff of how drastically the density is higher than its neighbors, but we choose the cutoff. So if we were to make a more significant cutoff, then we would be reducing this number of magic number clusters. So this isn't really indicative of some huge truth, but we chose the cutoff so that this would be maximally interesting, I think. So for these guys, there's a wide variety of point group symmetries in these clusters. This is the guy I was showing earlier. And again, just to reiterate that these magic numbers aren't the same, right? For these, they don't match. In most cases, they don't, except for here, they don't match magic numbers of spheres. Okay. Let me kind of skip through this. This is basically like building this guy, just to kind of show you guys that the cubic symmetry of the constituent particle really affects the symmetry of the cluster as a whole. So this is the innermost particle, and then you can this is the intermediate layer surrounding it, which is related to like a smaller n densest motif the n equals 12 motif in this case. And then this is kind of messy, but you can see when you build up around it, even though this is kind of a spherical cluster, right, it has to fit inside a sphere, there's clear cubic symmetry, so that the threefold axis along this isn't helpful, but yeah, the threefold axis along the diagonal is clearly visible in the outer shell. And then here's where I'll kind of start to wrap up here. I was kind of hinting at this earlier, but when you look at the more spherical platonic solids, you see that in a lot of cases, so for the magic numbers especially, these guys are matching to the densest sphere clusters. It's a different n, right? But this is still an icosahedral geometry. There's just one particle at the center in these cases. At n equals 21, it's kind of a similar story, and the n equals 38 cluster is special because it's cubically close packed, but it's also common among spheres and then the less spherical platonic solids. And so what do these motifs have in common? And what they have in common is that a lot of these motifs are spherical code solutions. So they're solutions to the Tammy's problem. This is a Dutch name, so I'm not sure how to pronounce it. But the Tammy's problem solution, that's a generalization of the Thompson problem that was discussed earlier. That basically, this always confuses me, but if we discuss kind of this optimization, it maps to, given a certain number of circles that you want to decorate a sphere with, you're finding the densest configuration of circles on the surface of the sphere. So these are called spherical code solutions. We were inspired to, I want to give credit to, there's this Torquato paper in 2011 that was discussing the relationship between spherical code solutions and local dense packing in terms of spheres. So when you actually look at common motifs across these different particle types, a lot of motifs are common, and most of the motifs that are common are spherical code solutions. So even the octahedra, in the case of n equals 7, form this solution. And at higher, this color is killing me, but at higher n, it's a similar story. These are all spherical code solutions. So I'll just kind of wrap up with where we are in the story right now. Basically, what we saw was that there's a wide variety of structures that are possible if you pack these faceted particles inside spherical confinement. And semi-regardless of particle symmetry, so for the more spherical faceted particles, the container is enforcing common cluster structures. So that's really potentially very interesting because these clusters are basically a class of motifs that are robust against perturbations in particle shape. So if you had particles that were kind of a little bit less spherical that you could only make in the lab or something, you could still expect, when you spherically confine them in an emulsion droplet or something, to generate like this type of cluster structure. So the container surface is really dominating the packing behavior for these sizes, which are really small sizes. So this is my funding, but these are the postdocs that I've been working with. So Greg Van Anders and Julia Shemushadze. I will never say her name correctly, but they're postdocs right now, and Daphne Klotzo was a postdoc in our group who has since moved on to bigger and better things. So with that, I'll take any questions, any other questions you guys might have. Thanks. Yeah.